Today we're going to learn about the basic derivative rules. So far we've been finding derivatives using first principles and limits, and today we're going to develop rules or take a look at rules so that we can not have to do that anymore and just use these rules to find the derivative. So the first one we're going to take a look at is the constant rule. So given that f of x equals 3, the derivative to that is 0. And let's just take a look at showing why that's the case for all constant c. So if we let f of x equal any constant c, then when I go ahead to find the derivative by taking a look at when the limit of h approaches 0, I can see that when our function at x plus h, or our function is at x, that I'm just going to have c. So I end up with the limit as h approaches 0 of c minus c all over h, which just gives me the limit as h approaches 0 of 0 over h, which is just equal to 0. So that means that our function, f of x, when it's equal to c, where c is a constant, then the derivative is always equal to 0. So now we're going to take a look at the power rule. And all of these derivatives you found in your homework. So for a function equal to x, our derivative is 1. Our function equal to x squared, our derivative is 2x. Our function equal to x cubed, it's 3x squared. And then x to the 4 is 4x cubed. And I'm hoping that we can see a pattern from our function to our derivative, and that's that pattern that you're recognizing is our power rule. We're just going to take a look at a quick proof why this is the case. Okay. So first we're going to let f of x equal x to the n, where n is a natural number. And then we're going to go ahead and find the derivative using first principles. So we have our limit as h approaches 0, and then we're going to have x plus h to our exponent n minus x to the exponent n all over h. So I want you to think about this numerator as a difference of squares or a difference of cubes that we're going to factor. So when I factor that numerator, I am going to go ahead and divide out the x plus h minus x part, and then we have that big piece left over. So if we had a difference of squares, we know that we would have the sum of the nth root of both of those over here, or the square root of both of those over here. Now, if we can take a look at the patterns for difference of cubes, and we can allow that exponent n to be any natural number, and when we factor out this piece right here, we're left with x plus h to the n minus 1 plus x plus h to the n minus 2 times x, okay, and then we get x plus h to the n minus 3 times x squared. And this actually keeps going on and on until we get to an exponent of 0 for the x plus h, right, which just goes to 1, and we end up with just our x term, okay, to the exponent n minus 1. So again, if that was a little bit confusing, that's okay. Just think of it as when we factored a difference of cube and what that looked like, what we got here for the factor, and what we got over here for the factor. Now all of this is actually over h, so I'm just going to go ahead and squeeze in a little 1 over h at the front there, just to save a little bit of room. So when we go ahead and simplify this, I can see that we are going to have, in this top part in here, we're going to have, hang on here. So we have our limit as h approaches 0, and let's just write the 1 over h in front here. And then this part right here, I'm going to end up with x minus x. So I'm actually just going to have an h there, okay? And then I have all of that stuff in the bracket there that we can take a look at in a minute, but let's just go ahead and see that those two h's divide. So we just have this big bracket left. So that gives me the limit as h approaches 0 of x plus h all to the n minus 1 plus x plus h to the n minus 2 times x, and we keep going that way until we have x plus h to the 1, and this is x to the n minus 2, plus, I'm running out of room here, I end up with x to the n minus 1 at the end. Okay, so now we can go ahead and sub in all of our h values equal to 0, and we end up with x to the n minus 1 plus x to the n minus 1 plus a whole bunch of x to the n minus 1, all of this being n times, which then we can write as n times x to the n minus 1. So if that was totally confusing for you, I wouldn't worry about it too much. I'm not going to ask you to go ahead and prove any of that. What we need to remember is this part right in here. Okay, so if I have a power, so x to any exponent n, where n is a natural number, then when I find the derivative, I go ahead and bring that exponent, right, down to the front, and then I subtract 1 into my in my exponents up there. Okay, so for example, we'll just do a quick example just to make sure that we're all on the same page. If I have f at x is equal to x to the exponent 6, then I know that f prime at x is equal to 6x and then to the exponent 5. Something to note is that this works the same for non-natural exponents, so you can refer to page 78 and 79 to take a look at another example with non-natural exponents. Okay, now we're going to take a look at the constant multiple rule. All right, so let's start off just taking a look at the derivatives of these functions. So if f at x is equal to 8x, then I know the derivative is equal to 8. And then this one is equal to negative 6x. Our next one is equal to, so if my function is 2x cubed, our next one is equal to 6x squared. And then our next one would be equal to 12x cubed. And this is very much related to what we did before with our power rule, except we had now we have a constant in front of our variable, and so hopefully we can see that we just, same as before, we bring that exponent down, but this time we multiply it with that constant, and then we do the same, we subtract from that numerator. So let's just take a look at why this works. So using first principles, so we're going to assume f at x is equal to a constant times another function g at x. And so when I take a look at finding the derivative, I'm taking a look at the limit as h approaches 0 of c times g at x, which gives me the limit as h approaches 0 of c times g at x plus h minus c times g at x all over h, which gives me the limit as h approaches 0 of c times g of x plus h minus g at x all over h, which we know is equal to c times the limit as h approaches 0 of all of this stuff, g of at x plus h minus g at x all over h, which I know is equal to c times the derivative of g. So when we're taking a look at a polynomial function, we can write it like this. If I have a constant times x to the exponent n, then my derivative is equal to my constant times n times x to the exponent n minus 1. Or f at x, if that's equal to a constant times whatever function g of x, I know that this is the derivative is equal to the constant times the derivative of g of x. Next, and lastly, we're going to take a look at the sum and difference rule. And this rule is pretty intuitive, so hopefully this isn't a big deal for anybody. So our first one here, when we take a look at the derivative of x squared minus 2x, I get 2x minus 2. The next one, x squared plus 5x, I get 2x plus 5. The next one I get 2x plus 1 plus 0, right, constant. And my next one I get negative 2. So taking a look at our definition, we can go ahead and let's just prove this really quickly. We'll let f at x equal g of x plus h at x. And so f prime at x is equal to the limit as h approaches 0 of g at x plus h, so it's a different h, x plus h, minus g at x, minus h at x, all over h, which gives me the limit as h approaches 0 of, we're just going to rearrange what's in the bracket here, g of x plus h minus g of x, all over h, plus h at x plus h minus h at x, all over h, which gives me the derivative of g of x plus the derivative of h at x. Okay? So our sum and difference rule that we're going to write down is that when we have two functions being added or subtracted, then finding the derivative is just the derivative of both functions separately, added or subtracted.